Hello learners, ready for a quick puzzle? Imagine giving a football a nice kick. Does it keep rolling forever like in cartoons? Nope. After a while, it slows down and stops. Why? Because some invisible player, force, is always in the game. In physics, force is simply a push, a pull, or even a hit. And it's shy, you can't see it directly, but you can surely see its effect. Push a trolley and it obediently rolls forward. Tug a drawer and it slides towards you. Even shapes are unsafe. Stretch a spring, it elongates. Press a ball, it flattens like a poor chap in a crowded metro. Mathematically, we capture this as F equals m into a. That is, force equals mass multiplied by acceleration. In short, heavier the object, tougher the job. Now picture this. Two friends, both stubborn, tugging a block in opposite directions with equal strength. What happens? Nothing. The block just sits there as if saying, "You guys sort it out, I'm not moving." This is the story of balanced forces. Equal in size, opposite in direction, they cancel out. Net force, 0. Change in motion, 0. The object either stays at rest or keeps gliding smoothly if it was already moving. Balanced forces are like two equally matched wrestlers, lots of flexing, but no one wins. The block stays calm, motion stays calm, and life stays calm. But what if one friend suddenly eats spinach like Popeye and pulls harder? Aha! The block moves in the stronger friend's direction. Welcome to the world of unbalanced forces. Here, the forces don't cancel out. The stronger side wins, leaving a net force behind. This net force brings acceleration, change in speed or direction. The equation is simple: acceleration equals net force divided by mass. So whenever you see something suddenly start moving, speeding up, or changing course, it's unbalanced forces pulling the strings. Alright, let's step into daily life. Ever tried pushing a giant cupboard across the floor? You push and push, but it acts like a stubborn old relative, refuses to budge. Why? Because friction is secretly matching your push force step by step. To kids pushing a cupboard from opposite sides with equal strength, the cupboard just smirks and stays put. And when you stop pedaling your cycle, friction steps in to balance your earlier push, slowing you down until you stop. Balanced forces are the masters of stillness and uniformity. They keep objects steady or moving smoothly without change. But crank up the effort and things get interesting. Push harder than friction, and voila, the box finally slides. Pedal harder on your cycle, and you beat friction to keep rolling forward with speed. Here, net force equals your push minus friction. If this net force is greater than 0, congratulations. You've created acceleration. More push, more action, more drama. So remember, whenever forces lose their balance, motion gains excitement. Let's put all this into action with numbers. Suppose you push a 50-kilogram box with a force of 200 newtons. Friction resists with 150 newtons. What happens? Step 1. Calculate net force. Applied force minus friction equals 200 minus 150, that's 50 newtons. Step 2. Apply Newton's second law. Acceleration equals net force divided by mass. So, 50 divided by 50 equals 1 meter per second squared. Result? The box accelerates slowly at 1 meter per second squared. Moral of the story: always calculate the net force first. Don't let friction fool you. So let's wrap this up. Balanced forces mean net force equals 0, motion remains steady, No acceleration. Unbalanced forces mean net force is not zero, motion changes, acceleration appears. Friction often plays the villain, balancing small pushes. Overcome it, and you set objects in motion. In short, balance sustains, imbalance transforms. That's why we need teamwork to shift heavy furniture, why cycles slow without pedaling, and why literally every motion change around you has an unbalanced force behind it. And with that, I hope you're now confident enough to explain balanced and unbalanced forces to anyone, even your younger sibling, while dragging their chair around. See you next time when we uncover Newton's first law of motion, the legendary law of inertia.